So this week, we're also going to be writing ionic formulas for those ionic compounds with transition metals. And so hopefully you remember that those transition metals, so if we take a look at them, see if you can locate on this chart some of those transition metals. And I'm just going to go through and circle some for you. What do you notice about these transition metals? Just take a moment and look at some of these transition metals here. And as you can see, I'm circling them. Well, hopefully you're noticing that oftentimes these transition metals come with Roman numerals and they have different charges. And you are exactly right. And that's going to be the basis for what we're going to be taking a look at this week. All right, so if you're taking a look at the periodic table, hopefully you're also, as you're thinking about the transition metals, remember that we are going to be thinking about the, sometimes called the B groups, or filling the d orbitals. We're going to be talking about the atoms right in here. And hopefully this is going to work because it hasn't worked so far. There we go. We're talking about all of these elements right in here. This is what we're going to be using this week. And you'll remember that these elements right in here, in that part of the periodic table, are filling their d orbital. Now, because the d orbital is large and a little bit complicated, oftentimes the elements can move those electrons around and have a variety of charges. And so that's what you're going to see here, that they're going to have these various charges, as we just saw in the last slide. And so again, there's our transition metals. They have properties similar to the group 1, group 2, and group 3 metals on the periodic table. So here's some ways, of course, that they're similar. They're shiny with that metallic luster that we've been talking about for the metals. They're good conductors of both heat and electricity. Some ways that they're different. Generally speaking, let's look at our alkali metals. Those were our group 1 metals with 1 valence electron. And those alkali metals are softer. Most of those alkali metals you can cut with a butter knife. You can't do that with the transition metals. They're much stronger and tougher. The alkali metals are generally lower in density, whereas the transition metals are much more dense. The alkali metals, like all metals, want to give away electrons to become positive ions. The alkali metals only want to give away 1 valence electron to become a positive 1 ion, whereas the transition metals want to give away various amounts of electrons to have various charges. So if a transition metal, and one transition metal could give away 1, 2, 3, or 4 valence electrons. So that means if it gives it away 1 valence electron, it becomes a +1. If it gives away 2 valence electrons, it becomes a +2. If it gives away 3 valence electrons, it becomes a +3. If it gives away 4 valence electrons, it becomes a +4. And one element can give away various amounts of electrons. So they can have various charges, as we saw at the beginning of this video. Remember, your alkali metals are going to react with water. The transition metals, as you probably saw in our kickoff video for this week, form very colorful compounds. These are what we use in most dyes and ink and places like that, the transition metals and transition metal compounds. If you take a look here at our Statue of Liberty, it's made from a transition metal. Hopefully you know the transition metal that the Statue of Liberty is made from is copper. And if we look over here at this picture on the left, you can see the Statue of Liberty as it looked when it was first put up hundreds of years ago there in the New York City harbor. And over time, what has happened is the copper has reacted with the oxygen in the air to become this, what we call verdigris color, this greenish color. And so there's an example of these transition metals becoming brightly colored and having a variety of different oxidation states. So how do we write these formulas for ionic compounds with the transition metals? Well, the first thing you need to do is to look at the Roman numeral next to the element's name. And this is going to tell you its charge. Then you find the charge for the other element, usually a nonmetal or a polyatomic ion. Count how many of each atom you need to cancel each other out to get to that zero charge, or use that crisscross method that we've been talking about. Then you simply write the symbols and the charges, include the number of each atom that you're going to need, or each ion that you're going to need to get to that neutral charge. Write the symbol for the nonmetal or the polyatomic ion, include the number as needed. If you've used the crisscross method, be sure to reduce those subscripts. So let's look at a couple of the, and so you do need to know the Roman numerals. So you may want to take your phone and snap a picture of this because you will need to know those Roman numerals. All right, so let's do a little bit of practice. So here we've got cobalt-2 and oxygen. So you'll probably remember that the first thing that we're going to want to do is write the symbol for cobalt and its charge. Since this is 2, it's a +2, and oxygen, which is a -2. Now you can do this one of two ways. You can look to see, do they equal 0? Do the math. Obviously they do equal 0. Or you can do the cross method. So you actually crisscross those charges. And so we wind up with CO2, O2. And of course you don't put the charges in there in the formula. And then you would have to reduce those if you're using that cross method. So there is our formula for cobalt-2 and oxygen. So we would always, anytime that we would be using that, we would always tell them that it's cobalt-2. Because cobalt could be cobalt-1, cobalt-3, cobalt-4. So let's take a look at another one. Here's iron and sulfur. So what would be the formula with iron-3 and sulfur? So once again, the first thing you're going to want to do is to write the symbol for iron. Of course, iron is Fe. Since this is iron-3, that's going to be 3+. And then sulfur. Our symbol for sulfur is S. If you take a look at the periodic table, you'll see that sulfur is a 2- charge. So now you got to figure out, does this equal 0? If you're in math class, obviously you're saying no way. 3+ and 2-, that's going to be a +1, so that doesn't equal 0. So that would not allow me to write my formula that way. So probably then you may want to use the cross method or the crisscross method. So next to that Fe, we would put a 2. Again, we're not going to put the charge in there with it, but there's our 2. Next to S, we would put that 3 that we see coming from the iron. And of course, you can always uncross them as well. So there we go. There's our formula. Take a look at it. Do we need to reduce it? Fe2S3? No, those are in the lowest whole number terms that we could have. So if you had this and you wanted to figure out what the charge of the iron was, you can always work your way backwards. You can say, oh, well, that 3 originally came from Fe, so that's iron 3. Just another way to take a look at that. All right, here's the next one for us to do for an example. This is copper-3 and fluorine. So once again, we're going to go ahead and copper-3. Copper is Cu, if you're looking at your periodic table. Since this is 3, this is going to be 3+. And fluorine, of course, we know that fluorine is in the halogen group. It's F with a 1- charge. So take a look at those two. Do they equal 0? No, if you're saying no. And so, again, another way you can do that is you can figure out how many fluorines you're going to need to equal the copper. And, of course, you're going to need 3. And then it would equal 0. So that's one way to do it. Or you can simply use the cross method that we've been talking about. So you can simply take these charges and cross them over. And so next to F, we would put a 3. Next to copper, we would put a 1. So it would become Cu 1 F 3. And now, of course, since we've used that cross rule, we need to reduce. So we've got 1 and 3. Obviously, what we don't need here is that number 1. So there's your formula, CuF3. Now keep in mind that that 3 originally came from our copper, so that tells us that that copper was a 3+ charge. All right, molybdenum 4 and bromine. So you'd need to take a look at this one and see if you can figure it out. This may be a great place to pause the video and test it out on your own, because I'm simply going to put this in here just like we've been doing all along. There you go. Now, of course, we're going to reduce. So obviously we get rid of that 1. So there we are. And I believe I have one more, maybe I have 2 more examples for you. Okay, so again, this may be a great place to pause the video, try it out on your own, see if you can get this. If you don't know the symbol for mercury, it is Hg. And that was our last example for this evening. So I hope that by this point in time, you're feeling pretty good about writing formulas with these transition metals.